Good morning, folks. So, a few things to play with today. I want to make sure we're all good and comfy with integration by parts, so I thought I'd maybe do one or two more problems like that. But then the main topic is going to be on trig integrals, which is the first section we're going to cover this week. New material. Just 1 second to get my stuff organized here. Integration by parts, trig integrals. And we may get into a little bit of trig sub this week, but probably not. So let's go ahead and get started. I see a few different people wanting a few different problems from the IBP homework. 5, 12, and 14. Seems like 12 is especially interesting. So let's look at a couple of those. Oh, I got kicked out of WebAssign, so I'm going to need just a second to sign back in. Let's get the .cam shut up. So of course, this is So we're going to focus mostly on trig integrals today, but first we'll do a few IBP problems. This is up now and in chat. I saw that we wanted 5, 12, and 14. So let's look at 5 first. Since this is coming from the homework on integration by parts, you can guess that you will need to use integration by parts. That's fairly, oh, shit. Sorry, I just kicked over my coffee. You can guess that we'll need IBP. And your LIPET rule will help you here. So my LIPET rule for choosing U and dV in integration by parts starts with an L, and that L stands for logarithm. Since this integrand does have a logarithm in it, according to my LIPET rule, I should use that piece for my U and everything else for dV. So that's what we'll do. We're going to get started with our IBP table. U is going to be the logarithm term, which is ln of the square root of x, which means dv has to be everything else. And in this case, that's just dx. du, the derivative here, is going to require using the chain rule. So that's 1 over the square root of x times the derivative of the square root of x, which is, I'll write it like this first, because I think that's how most people will think of it. So remember, the derivative of a logarithm is 1 over the inside of the logarithm times the derivative of the inside, right? So 1 over the inside times the derivative of the inside, and then I've got my dx. If dv is equal to dx, then v is equal to x. And I'm trying to get into the habit of drawing my v's in this more angular form, so folks don't dislike them so much, so they look a little bit less like u's. I'll do my best there. This guy can be cleaned up, though. Do you agree that that's the same? This 1 over square root x is like my 1 over u from the derivative of the log. This is the derivative of the outside. And this is the derivative of the square root of x, is the derivative of x to the 1/2, taken using the power rule. So together there, that chain rule thing is what I get. And this is the same as 1 over 2x dx. So I think the challenge there might be in correctly using the chain rule to get the du term. I'm not sure, but if I had to guess, I would say this is where maybe some of us had a hard time. So questions up to here? Questions on how I found du? Okay. So then according to my IBP formula, I take u times v, and then I subtract from that the integral of v times du. And you see that IBP actually handles this really quickly. So the x's here will cancel, and you get x times the natural log of the square root of x minus 1/2 integral of just dx. And the integral of dx is x. So this is x ln x, or sorry, x ln root x minus 1/2 x plus c. And the work is all in calculating du. So remember that the ln of some stuff, I usually would use u here, but I don't want to confuse things. Ln of f of x, all primed, is 1 over f of x times f primed of x. Right? It's a chain rule thing. Any lingering questions about this one? So the Lipet rule is a hierarchy. You start looking for L's. If there aren't any L's, you move to the I's. If there aren't any I's, you move to the P's. So that Lipet rule is more than just like, if there's one of these, use it. If there isn't, don't. It tells you which one you should pick first. So if you had both a polynomial and a logarithm, then you would use the logarithm for u and dv to be everything else. And yes, and then the second question there was what happened here. So I canceled the x's, popped out the 1/2, and then I'm just left with the integral of dx. Yeah, the x's in the integral cancel. Right, exactly. Yeah, it's like the word I like to use is hierarchy, but yeah, like a tiered list. So if there are logarithms, use that for u, everything else is dv. If there aren't any logarithms, then you move down. But you only move down if there isn't the thing above. So if you had a logarithm and a polynomial, the log would be your u. If you had an inverse function and an exponential function, then the inverse function would be your u. All right. I did kick over my coffee, so I'm going to go refill this. I'll be right back, and we'll look at number 12. Number 12, I suspect, is the looping integral. Oh, no, it's not. Okay, yeah, 12 isn't bad. I'll be right back. We'll work on number 12 together in just a second. Okay, let's try this again. This time, no coffee on the floor. So homework 3, number 12, is asking us to integrate from 1 to 2 the square of the natural log function divided by x cubed dx. So looking like this down here. We could try making a substitution first. That would gobble up one of those x's from the denominator, but then I'd still have 2 of them left. So I'm not sure that the substitution first is the way to go here. We can just jump in with our IBP. Cross our fingers, hope everything works out. Let's try that. So I would choose u to be my logarithm piece, which is the ln of x all squared, and dv to be everything else, which is 1 over x cubed dx. du, again, is going to require a chain rule. Looking like this. I bring the 2 down, reduce this power by 1. That's 2 times the log of x raised to the first power, which is just the log of x. And then I multiply by the derivative of log x, which is 1 over x. And then to pass from dv to v, I need to integrate. Integral of 1 over x cubed, think of it as a power rule thing. That's x to the negative 3. So I'll increase the power by 1 and then divide by that new power. That's negative x to the negative 2 over 2. All right, x to the negative 3. If you add 1 to that power, you get negative 2. So if you want to, you could write this as negative 1 over 2x squared. Tammy, what are you crying at, Bubba? Sorry, my dog just came in and started crying. What's on? Oh, did mommy get out of bed? No more snobbles. Okay, so let's see how this looks. If I just run my IBP here, I have my u times v, so that's ln of x all squared divided by 2x squared with a negative out front, and this needs to be evaluated from 1 to 2. And then I subtract from that the integral from 1 to 2 of v times du. So here the 2's will cancel. V times du. Du has a 2 upstairs, v has a 2 downstairs. Those are gone. I have this negative. I have ln x upstairs, and I'll have x squared times x downstairs. So this is going to be, I'll write it in separate steps so we can follow what's going on. 2 ln x over x times -1 over 2x dx. Sorry, I kind of cramped that in there, but in my next line I'll do some simplification. We should go ahead and evaluate this also. So if I plug in a 1 down here, the natural log of 1 is 0. So the 1 doesn't contribute anything. But when I plug in the 2, I will get something. So this will be negative ln of 2 squared divided by 2 times 4, which is 8. And then from that, I'm subtracting this integral, and now I'm going to clean up this integrand. So like I said, these 2's will cancel. This negative, I can pop out front to make this minus a plus. And what's going to be left here, oh, this should be a 2x squared down here, yeah. So the x squared and that x will give an x cubed, so I'll have the integral from 1 to 2 of ln x over x cubed dx. Everybody see what's happened here? Zoom it out just a tiny bit. Okay. So now I need to look at the ln of x over x cubed and see if I can come up with an attack for that. But the only thing I have to integrate natural log functions is integration by parts. So this suggests I'll need another run of IBP. In fact, if you made this substitution that I suggested at the start, z equals ln x, this would turn into an exponential times a polynomial. So the repeated applications of integration by parts here, not too surprising. So one more run of IBP should finish the job. I will copy down what we have so far. I have the integral from 1 to 2 of ln of x all squared over x cubed equals negative ln of 2 squared divided by 8 plus integral from 1 to 2 ln x over x cubed dx. Okay, sorry about the coffee stain. This guy now requires some integration by parts of his own. So I build another IBP table. Again, I pick u to be the logarithm function. This time it's just ln x. dv is going to be everything else. That's still 1 over x cubed dx. du is now free of logs. It's just 1 over x. And v is the same as it was before. Negative 1 over 2x squared. So the dv to v stuff is power rule stuff. I'm not showing the details here, but if you want to take your time and step to the side to integrate 1 over x cubed, you will find that you get negative 1/2 negative 1 over 2x squared. Which means that the line above can be written as negative ln 2 squared over 8 plus u times v, which is, all right, like this, negative ln x over 2x squared minus the integral of v du. My v has a negative in it, which will make this a plus. And then I've got 1 over 2x squared times 1 over x. That's 1 over 2x cubed dx. Thank you. Yeah, we do need the bounds here. I almost made that mistake. So we need to evaluate each of these pieces from 1 to 2. Very good. All right, so we're almost there. Again, when I evaluate this piece at the lower bound of 1, the numerator is 0, so I won't get any contribution from that. I can pop the 1/2 out of the other integral, so this is negative ln2 squared over 8. The upper bound here will give me negative ln2 over 2 times 4, so that's negative ln2 over 8. And then I have my plus 1/2 integral x to the negative 3 dx from 1 to 2. And the x to the negative 3 integral we've done a few times. I should use these little primes too. So this 1/2 is going to come along for the ride. The integral of x to the negative 3 is negative 1 over 2x squared. And he will be evaluated from 1 to 2. So we're almost done. Here I do get a contribution from both the upper and lower bounds, so we'll be a little bit careful. Negative ln2 all squared over 8 minus ln2 over 8 plus 1/2 times. When I plug in my upper bound of 2, I will get negative 1 over 2 times 4 is 1/8. And then from that, I'm going to subtract what I get when I plug in 1, which is negative 1/2. Finally, that's negative ln2 all squared over 8 minus ln2 over 8. Let's clean this up. This is the same as 1/2 minus 1/8. 1/2 is 4/8, so that's 3/8. And you could write that as 3/16 if you wanted to. Okay, so this one took a little bit of time, 2 runs of integration by parts. But we had a lot of stuff showing up repeatedly, like the dv to v step was identical in both. And then we saw that same integral show up again at the very end. Any questions about this guy? See, it doesn't look like I can get the whole thing on the page at once here. So any questions about the stuff on the first page, the first run of integration by parts? Yeah, I see something here in the chat. Yeah, so Simon makes a correct observation that you can plug in the bounds at the very, very end if you want to. But my advice is to not do that. My advice is to evaluate as you go, because oftentimes this thing will evaluate to something that just takes less space to write after you do the evaluation. For example, the lower limit here in both of the evaluation steps that came early contributed a 0. So while you can wait till the end to evaluate, my advice would be not to. And then the question about the plus c, yeah, because this is a definite integral, not an indefinite one, because there are bounds here, we don't ever need a plus c. Okay, there was one other problem that was requested, number 13. We can take a look at that guy. But before I do that, I want to show you what I was talking about. Oh, 14, not 13, okay. Before I do that, I want to show you what this integral would turn into if you make a substitution. So there's a pretty natural substitution to try for with this integral. And I just want to show you how that would go. And that should explain why we ended up doing the repeated integration by parts. So this started as, oh hell, where did that go? Log squared over x cubed, right? Yeah. So this is still homework 3, number 12. Just looking a little bit deeper at it. Integral 1 to 2 log x all squared divided by x cubed dx. What happens if I make the substitution z equals ln x here? dz will be 1 over x dx. My limits are not going to be too hard. 1 goes to 0. 2 goes to log 2. If I do that, I'll have the integral 0 to ln 2. Ln x squared just becomes z squared. One of the x's from downstairs will be eaten up by the differential, but I still have 2 x's down there. So I'm going to do this thing here, where I mix the variables, which we shouldn't do. So I've absorbed one of the 1 over x's into my dz. And now if I take this guy and I solve him for x, you see that e to the z is x. So I could write this as the integral from 0 to the natural log of 2 of z squared over e to the z squared dz. And then that I can just do a little bit of algebra with to see is the same as z squared times e to the negative 2z dz. So you really do have a polynomial times an exponential function here. It's just hiding underneath this substitution. And you see that the polynomial, when you do that substitution, is a degree 2 polynomial. That's why I needed 2 runs of IBP to finish the integral. Now, is it worth it to make this substitution before doing the integral? I don't think so. I would say just jump in. But if you're wondering why that integral went the way it did when we jump in, this is why, right? So a polynomial times an exponential, or polynomial times trig, you'll always have to run integration by parts the number of times that matches the degree of the polynomial. All right, I think that's enough time looking at number 12. Again, I don't necessarily recommend this. I'm just showing you why that took 2 runs of IBP, because hiding underneath it was really a polynomial times an exponential. We said we did not want to see 13, but we did want to see 14. So 13 and 14 are both similar in spirit to what we just did there, where you make a little substitution and then run some IBP. Caesar asks a really good question. How do we know when it's worthwhile to try a substitution before the by parts? I would say if there's an obvious substitution, a substitution that will go through really cleanly, that's worth trying. Like for example, in number 14, I'll rewrite that sine of 2t using a trig identity, and then the integral that's staring at us after doing that is like begging for a substitution. 13 here, the cosine of theta squared and this theta cubed, again, kind of begging for the substitution, z equals theta squared. You know that one of these thetas in the theta cubed will get eaten up by the differential if you substitute for the theta squared, because the derivative of theta squared is 2 theta. And that would leave theta squared here, which is exactly what you wanted to substitute for. So maybe instead of working 13 and 14 completely, I'll make the substitution in both and then work one of them completely. So this is homework 3, number 13, and I'll just do the substitution here. We're integrating from the square root of pi over 2 to the square root of pi, and those bounds also kind of suggest a substitution. 7 theta cubed cos theta squared d theta, and I'll switch you back to the dot cam. Okay, this is a theta squared there. So there's kind of two things in this that make me think a substitution is worthwhile. First, the bounds. Those aren't super nice numbers, but they are square roots of super nice numbers, which suggests if I squared them, things would get nicer, and the way you end up squaring the bounds is by substituting, you know, z equals theta squared. The other thing I see here is that my integrand is ripe for a substitution. So I pop out the 7. I've got the integral from square root of pi over 2 to the square root of pi. And I can rewrite this as theta squared cos theta squared times theta d theta. So you see here, this looks like it wants you to substitute for theta squared. You've got a function here where instance of the variable has the variable squared, and then you have exactly what you would need to make the substitution work in the differential. I hear someone asking a question. Yeah, we are going to do 14 too. I just want to show you what the substitution looks like in both. Was somebody trying to ask a question through the mic? So theta cubed, I split into theta squared times theta. One of them I left at the end to help us see why the substitution is a good idea. So when we do that, we see here, every time theta shows up, it's showing up squared. And then this is exactly what I would need to substitute z equals theta squared. So if I do that, my dz is 2 theta d theta. My limits go from the square root of pi over 2 to just pi over 2, and the square root of pi to just pi. See, it's just that under this substitution, everything gets nicer. My 7 out front is going to come along for the ride, and I get the integral from pi over 2 to pi of z cos z times 1/2 dz, and the 1/2 can come out. So that looks much nicer to me. So this is a good example of a problem where doing the substitution first really does clean things up a lot. This integral looks a lot more approachable to me than this integral. And we could see that by kind of thinking of theta cubed as theta squared times theta. So that's how I would know ahead of time to make that substitution. When I look at this integrand, it looks like it would be nice to substitute for theta squared, Also, the bounds look like they would be nice to substitute for theta squared. And when I implement the substitution, the resulting integral looks like it's easier than the original. So I'm not going to follow through with how to solve this integral. This is straightforward IBP. This is your polynomial piece, so you'll pick u to be z, and dv will be everything else, cos z dz. Just don't forget to evaluate between the bounds. Number 14, I will do the entirety of. But it starts off similar. So here we've got e to the cos t sine 2t dt from 0 to pi. All right, this isn't a minus sign, it's just a smudge. My pen ran a little bit. The trick here is the double angle identity for the sine function. And this is a nice problem to work today because we're coming into section 7.2, which is all on trig integrals, and you must know your trig identities. Am I looking into the camera harshly enough? You must know your trig identities. Sine 2t is 2 sine t cos t. That's the double angle formula for the sine function. So this integral is equal to 2 times the integral from 0 to pi e to the cos t times cos t sine t dt. And again, here I've got a function that I would like to substitute z equals cos t into, and here I have exactly what I need to make that substitution. So we use this identity. And having plugged 2 sine t cos t in for sine 2t, I see that the integral would respond well to a substitution. Namely, I want to let z be cos t. dz then is negative sine t dt. My bounds will change. When t is equal to 0, z is equal to the cosine of 0, which is 1. So the bound 0 goes to the bound 1. And the bound pi, the cosine of pi is negative 1, right? So you got to know your unit circle. You got to know your trig identities. No escaping it, especially in the stuff we're doing this week. When I drop that substitution in, my integral becomes 2 times the integral from 1 to negative 1 e to the z times z times negative dz. Right? Sine of t dt, that's the negative of dz. Now this negative, I could bring out front. I'm going to be a little bit verbose here because then I'm going to use it to flip the bounds. But I want to make sure we can follow everything that's going on. I'll write the integrand as z times e to the z because it looks nicer. The z out front. And then my last step before doing the IBP is going to be to soak this negative back into the integral by flipping the bounds around. So this is the same as 2 times the integral from negative 1 to 1 of z e to the z dz. And again, this looks a hell of a lot nicer than this. It still requires IBP, but it's the same spider senses that you use when choosing your substitutions back in section 5.5 that you'll use to determine whether or not to make a substitution here in 7.1. The sine t got eaten up by this differential term right here. dz is negative sine t dt, which means negative dz is sine t dt. So this piece right here is negative dz. These are good questions. What else are we thinking? Can we solve it by symmetry? Good question. I don't think so. This is not an odd function, nor is it an even function. So if this were an odd function, then I could say that the integral is 0 by symmetry. But unfortunately, the e to the z piece ruins any even or odd arguments. So I'm not aware of any solutions via symmetry here, at least not quick ones. You could have left the bounds as they were, yeah. You could have left this negative out front here in front of the 2 and left the bounds as 1 to -1 in that order. There's nothing wrong with that. I just think it looks prettier like this. What else? What else are we thinking? I love this. This is really good. I want to hear your thoughts. I want to hear your questions. I enjoy this conversation. What else are we thinking? Right. Yep. So just like Simon said in the chat, the next thing is going to be some integration by parts. I've got a polynomial times an exponential, so I expect to have to run integration by parts however many times the degree of this polynomial. Thankfully, it's a degree 1 polynomial. So the move here is IBP. U will be my polynomial piece, which is just z, and dv will be everything else, which is e to the z dz. du is dz, and v is e to the z. Yes, exactly, yep. So I need to remember to open up a big parentheses. That 2 is going to have to get distributed to everybody. U times v is z times e to the z. I know I've been using the brackets for evaluation, but sometimes we like to just use a vertical line. And in this setting, I think it looks a little bit cleaner to just use the vertical line. So I'm going to do that instead of the brackets to just keep things looking clean. And then we'll have minus the integral from -1 to 1 of v times du, which is just e to the z dz. My next step is going to be to cook up the antiderivative here, which is easy, and then we'll evaluate. I'll also evaluate this piece. So I have 2 times z e to the z from -1 to 1 minus 2 times the antiderivative here is just e to the z from -1 to 1. So I distribute the 2 and cook up my antiderivative in one step there because the antiderivative is very easy. And now the evaluation. So this piece is 2 times 1 times e to the 1 is just e minus -1 times e to the -1. And then I subtract from that 2 times e to the 1 minus e to the -1. So this is really 1 times e to the 1, right? So overall, I've got 2e minus 1 over e, so that's 2 times e plus 1 over e minus 2 times e minus 1 over e. And what can we do with all of this? I guess we factor out the 2. Yeah, so I didn't need to distribute that. Combine our like terms, so I've got the e showing up positive here, showing up negative here. I'll write it all out. Why not? 2e plus 2 over e minus 2e plus 2 over e. So these guys cancel, and we get 4 over e. Bring this back down, zoom out a little. Questions on this fella? Problems like this are fun. Substitute and then IBP. You may remember one of the challenge problems I gave you. Yeah, sure, Ryan, just come by the office hour after this. Notice when we see something a little complicated at the start, it's not a bad idea. So when we get to section 7.5, I'm going to teach you guys over the next 2 weeks a bunch of different tricks for integration, right? One trick is U-sub, another trick is IBP. I'm going to teach you like 3 or 4 more tricks. And then when we get to section 7.5, I'm going to show you guys how I choose which trick to try first. Right now, we only have 2 tricks, substitution and IBP. So if you look at the integral and it doesn't appear right away to be an obvious IBP, then you should look for a substitution. Yeah. Another problem like this is the challenge problem I left you guys at the end of class last time. You may recall. And this is something I used to put on my exams, but I don't think would work so well in the online format, so I'm comfy sharing it with you. If I wanted to integrate the cos of the ln of x, that's a really good example of a U-sub followed by a IBP. I'm going to have to take this. I'm sorry. Hello? Yes. Oh, hey, Jennifer. I'm doing good. Okay. Yeah, I'll be here all day. I'll spell it for you. It's quite long. It's P like Paul, F like Frank, E-I-L, S like Sam, T like Tom, I-C-K-E-R. The street is 43rd Street. I was afraid he heard that wrong. Yeah, 43rd, 4-3. The complex is South Fork Oaks. Yeah, as far as I know, I will be here all day. Yep. Okay, could you give me any sort of time estimate? Okay. That'll work for me. All right. Thank you. Bye. Sorry, I woke up this morning and the AC in my apartment died overnight, so it was real fucking hot. So that's a little bit urgent. So you may remember this challenge problem I gave you guys at the end of class last time is a great example of a substitute and then do integration by parts thing. Because this integrand looks so gnarly, it's the cosine of some stuff, but the stuff is complicated, I want to try to substitute for the inside of the cosine function. When I do that, though, I get this differential, the 1 over x term, which I don't have floating around in here. So I can multiply both sides of this differential relation by x to find that x times dz is equal to dx. And then in order to make things go, I need to write this x in terms of z. So my differential is really e to the z dz. So x dz equals dx is the same as e to the z dz equals dx, which would mean this guy becomes cos z times e to the z dz. And then that would be a looping problem, right? That's an IBP problem that we did last time, e to the z times cos z. So this is another good example of a challenging substitute then run IBP. I'm not going to go back through the cos z e to the z integral. If you want to see that, look at the video from last time. That was one of the looping problems we did. Is there anything else from integration by parts land that you guys would like to talk about before we move to section 7.2? Any questions or concerns? It can be a concept thing or a particular problem, anything at all. Okay. Okay. Then we are going to begin on section 7.2. So you are going to have a new homework this week. I haven't opened it yet, but I will open it as soon as I get it ready. It'll probably be just a little bit after class there. I'll try to get that published while I'm doing the office hours. Naz asks in chat, do I know of a website for practice problems? Yeah, look at the modules section in our Canvas page. You'll see that I send you often to Paul's online notes. That's a math professor named Paul at Lamar University. He has lots and lots and lots of practice problems, lots of them. Another really good source of practice problems is the textbook, right? This thing. Now, I don't want you to spend $300 on this unless you know you want it and you want to have it for the rest of your life, which is why I'm happy to share with you. Where is it? This guy. So this is the same book. This is a PDF of Stewart's Calculus 8th edition, Early Transcendentals. So if you're looking for a source of extra problems, I would come here and look at all of these, right? What I did when I was in calculus class, I solved every problem. I went through the book and solved them all. And that was really, really helpful for me. And I would recommend you doing the same. Now, if you don't have a physical copy of the book and you don't like the ebook in WebAssign, I don't blame you for either of those things. Reach out to me via Canvas message and I can help you get a copy of this PDF. Sorry, I'm going to have to answer this again. Hello? 32607. All right. Thank you very much. Okay, sorry about that. So let's come back to what we were doing. What were we doing? We were talking about 7.2. But yeah, Paul's online math notes is a good source of extra problems. Your textbook, though, would be my first go-to. And if you don't have a hard copy, you want an e-copy, hit me up. Seven 7.2 is all about trig integrals, which are integrals of trig functions. We're going to start with the basic 6, right? How to integrate sine, cosine, secant, tangent, cosecant, cotangent. And then we're going to talk a little bit about how to handle combinations, certain combinations, meaning products of sine and cosine, or powers of products of sine and cosine, and powers of products of secant and tangent. It turns out any trig integral can be broken down into things like that. So once you know how to handle those, you'll be in good shape. But before we even touch that stuff, you got to know your trig identities. So some identities that we use all the time. First, there's the Pythagorean identities. These are sine squared plus cosine squared equals 1. And if you divide through everywhere here by cosine squared, you get tan squared plus 1 equals secant squared. And if you were to divide through the original guy here by sine squared instead of cosine squared, then you would get 1 plus cotangent squared equals cosecant squared. Hopefully everybody remembers these. These are kind of the three most fundamental of all trig identities. Then we've got double angle. And these are sine 2 theta equals 2 sine theta cos theta. And cos 2 theta equals cos squared theta minus sine squared theta. There are other ways to write the cosine of 2 theta. There are double angle formulas for the tangent function, but those are really the only ones we use. And then we have half angle. These are sine squared theta equals 1/2 1 minus cosine 2 theta. And cos squared theta equals 1/2 1 plus cos 2 theta. Okay. So these are the absolutely necessary trig identities to get through section 7.2, and we'll be using them elsewhere in the class. You got to know these. You got to know these cold. You have to know these so fast. Should never have to waste time conjuring these. So if they're not things that are like burned into your skulls already, work through the homework. Write down the identity on its own each time before you use it, like outside the integral, like I did here. I said, like, I'm going to use, it's on the other page. I said, I'm going to use this identity. I wrote the identity and then I used it. That sort of thing will help you remember. And if they're still not burned into the point where you can just call them up immediately once you're like halfway through the homework, then I would consider making some flashcards. I don't like flashcards, but I know some people do. So the main things we're going to be going after, our goal, is to be able to integrate anything expressible as a power of sine times a power of cosine and a power of tangent times a power of secant. It turns out that any mishmash of trig functions can be split up into stuff that looks like this. No, it's a little bit weird. So the way I write these identities here is the way that they're useful in the integral. We actually use them to take even powers of sine and even powers of cosine into lower powers of cosine. So you could write sine squared of theta over 2 equals 1/2 times 1 minus cos theta. But instead, I write it as theta over here and 2 theta over here. The other double angle formulas for cosine actually come from these things that we're calling half angles here. There's no difference between a half angle identity and a double angle identity. They're the same thing, right? On one side, you've got theta. On the other side, you've got 2 theta. Same thing as saying on one side, you've got theta. On the other side, you've got theta over 2. But this is the way I write these because this is the way they're useful for our integrals. Yeah, in your trigonometry class, you probably saw these with like theta over 2 here and theta here. It's the same thing. If you multiply theta over 2 by 2, you get theta. If you multiply theta by 2, you get 2 theta. So it really does say the same thing. All right. So how are we going to get at these things? I want to be able to do integrals of anything that looks like this, so like sine cubed times cos to the 10, or tan to the 4 times secant cubed. I want to be able to do all of those. We break them down into these two families, and then each family we break down into a few cases. There are easy cases, and there are less easy cases for each of the two families. Before we dig into that, I want to go over the integrals of the 6 basic trig functions, because that's kind of at the heart of this. So first, we need to know. Well, actually, no, we don't. Let's just dive in. Let's just dive in, because we know that shit. The only new one is the integral of secant, but we did that the other day. So we're going to talk about integrals of the form sine m theta cos n theta d theta. And I'm going to be a little bit sloppy here and not write the parentheses around the thetas, because there's never anything weird going on here. The two cases we consider, so we can be broken, these can be classified into two cases. The first case is at least one of m and n are odd. If at least one of them is odd, then we're going to make a u substitution. Here we will use substitution. The other case is neither of them are odd, which means both are even. And here we will use half-angle identities. This one, the substitution approach, will require use of Pythagorean identities. Okay, so this is a very high-level approach. What exactly is it we're going to do will depend on what m and n are. Which one is even, which one is odd, something like that. But at a high level, if both of the powers are odd, you're going to end up doing a u sub or z sub, and you're going to end up using some Pythagorean identities, some stuff like sine squared plus cos squared equals 1. If neither of the powers are odd, that means both of the powers are even. And in that case, we just beat the shit out of the thing with half-angle identities until we get to a place where we can perform the antiderivative step. I'm going to tackle a case 1 integral first, or a few case 1 integrals first. So best way to learn is just by examples. Let's do it. Let's try this. Sine cubed times cos squared. The nice thing about the sine cosine integrals is that the derivative of sine is cosine, and the derivative of cosine, not exactly sine, but it's very, very close, right? It's the negative of sine. So these are often good places to try substitutions. If one of the powers is odd, as is the case here, then you're going to grab an extra copy of this guy and set it aside for substitution. So I'm going to write this as integral sine squared theta times cos squared theta times sine theta d theta. So if one of the powers is odd, you grab a copy of that odd guy and set him aside with the differential. He's going to be used for the substitution, which means I'm going to be substituting for cosine. So then I let z be cos theta. My dz here is negative sine theta d theta. And since it's an indefinite integral, I don't have any bounds to worry about. So what I get here is sine squared theta times z squared times negative dz. But I don't like this. This is bad, right? How do I write this? In terms of z. Because I need that, right? I can't have mixed variables in a substitution. When I do a substitution, I need to replace everything with the new variable stuff. That's where your Pythagorean identity is going to come in. We know sine squared theta plus cos squared theta equals 1, which means sine squared theta is 1 minus cos squared theta. And cos squared theta is z squared. So this is 1 minus z squared. So my integral is really equal to integral 1 minus z squared times z squared. We've got a negative from the differential and my dz here. Okay, so your powers of sine times powers of cosine integrals, if one of the powers is odd, or if either power is odd, it doesn't matter, they can both be odd, you'll grab a copy of one of the odd powered functions to set aside with the differential for a substitution. What's nice about that is that means that the power that's left will be even. If you subtract 1 from an odd power, you always get an even power. And an even power of sine can always be written as a power of cosine or a polynomial in cosine using the Pythagorean identities. From here, the problem is easy. This is negative integral, distribute the z squared. You get z squared minus z to the 4 dz, which I'll continue down here. That's negative z cubed over 3 minus z to the 5 over 5. Like I said, I really don't need, we'll do it like this, plus c. And that's negative, I'll distribute my negative now and replace z by what it is, cos theta. So that's negative cos cubed theta over 3 minus cos, minus will make plus cos to the 5 theta over 5 plus c. This is the nice case. At least one of the powers being odd in your sine cosine integrals, that's the nice case. Usually I would not write this step. So I want to do one more of these where we're not kind of discovering, but I just show you how the problems usually run. So I wrote this all out in this way because I want you guys to go through that discovery process. Do we see where everything's coming from and why everything came out the way it did? Maybe better phrase, are there any questions about why things came out the way they did or any of these steps? It's really not too bad. It's really just U sub. It's regular U sub shit. The only difference here is that we're making use of a trig identity along the way. So let's try one more like this. Let's try one more sine cosine integral where at least one of the powers is odd. So here I have sine to the 4 theta times cos cubed theta d theta. It's a sine cosine integral where one of the powers is odd. As in the other problem, I'm going to grab one copy of the odd-powered guy and set him aside with the differential. So this is sine to the 4 times cos squared times cos theta d theta. This time I'm going to use the identity before I make the substitution, so we never have that mixed variables thing. I'm going to rewrite this as 1 minus sine squared theta, because my goal here is to substitute for sine. That's why I set aside that cosine. So this is the integral of sine to the 4 theta times 1 minus sine squared theta times cos theta d theta. And now this integral looks like it's begging for a substitution. That integral wants me to substitute for sine. So I let z be sine theta. dz is cos theta d theta. And this becomes the integral of z to the 4 times 1 minus z squared dz. The nice thing is that these will always result in a polynomial. Polynomials are easy to integrate. So these are really fairly simple problems. Sine cosine integrals where at least one of the powers are odd are fairly simple problems that will always lead to the integral of a polynomial. Distribute the z to the 4. So I get z to the 4 minus z to the 6 dz. And then I integrate. So that's z to the 5 over 5 minus z to the 7 over 7 plus a constant. And that is sine to the 5th theta over 5 minus sine 7 theta over 7 plus c. And that is the job done. How am I doing on time? Oof, we are out of time, aren't we? Okay. That's all right. We'll pause here. I want to recap, so I'll beg you to be patient with me just for 1 minute. So sine integrals like sine m theta cos n theta d theta. How do we do these? 1. If either m or n is odd, set aside one copy of the odd power function with the differential. Then write the remaining powers in terms of the other function. Using Pythagorean identities. Finally, substitute for the other function. So this is our strategy for dealing with these guys, if at least one of the powers is odd. So if the power of sine is odd and the power of cosine is even, you would set aside one copy of sine. your goal is to substitute for cosine. The sine theta that you set aside is what you'll use in the differential with your substitution. What you would have then is an even power of sine times some power of cosine, maybe even, maybe odd, I don't care, times sine theta d theta. The even powers of sine, which will be left because they're even, can be written using the Pythagorean identity in terms of cosine. So then you'll have some mess of stuff involving cosine here, a power of cosine here, and then sine theta d theta. So your move would be to substitute for cosine. If it's the other way around, then you just switch the roles of sine and cosine. So if the power of sine is even and the power of cosine is odd, just like in this last problem, you'll set aside one copy of cosine, rewrite the even powers of cosine which are left in terms of sine using the Pythagorean identity, and then substitute for sine. Next time we're going to look at how to handle the case where both of these are even, and we'll also look at some situations where both are odd, and I'll talk to you about which one you want to substitute for then. But I think it's a good place to stop for today, so we'll go ahead and stop it here. I am going to have an office hour starting in just a few seconds. If you need more time on the homework, just go ahead and submit an extension request, and I will go through and grant those this afternoon. Just be aware that there's a new homework that's going to open up today, so you want to wrap that shit up quick. I think that is everything. Any last minute questions for me, guys? Okay, so then this is where we will pause for today. If you want to talk to me about anything specific, come by my office hour. I'll be starting in just a few minutes, and keep an eye out for the new homework, which will drop today. All right, I hope you guys have a lovely afternoon. And remember what I said about the text. If you need that PDF, just reach out to me.